Okay, one of the questions that arose just a few minutes ago is whether or not to switch the course meeting from today to Wednesday. That we will settle that when I send a mail, and if I get a positive response from everybody, then we can certainly do that. It will not affect the camera capture, so no problem as far as that is concerned. Now, some of you have taken some location-related courses probably in the past. Some of you did not. Let me see. I just know John here, who took just one course in facility layout and location. We covered some location problems to some extent in that one. But other than that, anybody else who's taken a... Yes, you took 579. Okay, so I'm going to adjust my speed basically for everybody who is a newcomer, which includes almost everybody, okay? And some of you are already doing some research on this, working with me, so this course will help a lot for that research as well. Now, when we talk about facility location problems, basically this is going to be a little bit just the introductory stuff here. Basically, what we have is we're trying to place or locate some service facilities or production facilities in some space, which typically includes a geographical region, to service some demand points or some regions that will receive service from these facilities. Now, that's the basic structure. So when you start providing service to a bunch of demand points from a given facility, typically you have to overcome a certain amount of distance to get from where you are to wherever the service is required. Now that distance, if you're working, for example, in geographical space, in two-dimensional geographical space, in that case, of course, you may want to go using a straight line, the Euclidean distance. However, you typically cannot do that. Why? Well, if you're flying, it's basically a straight line distance. Of course, if you're at the home base of the airport from where the flight will take off, and there's an airport also at the point where you want to deliver the service. However, even that is not a Euclidean distance because you have to go up and then come down. Nevertheless, you can approximate that. Now, if you're using surface transportation, of course, you have to restrict your movement to either highways or to railroads, okay? But in either case, you can't really follow a straight line path. You have to somehow follow whatever path might be available. So there's typically an underlying transportation network of some sort on which you have to restrict your movements to. And given that transportation network, if you want to go from point A to point B, from wherever you are to the point of delivery of the service, what do? If there are no other restrictions, you just take the shortest possible way, or the particular path which gives you the least amount of distance, okay? So for such problems, typically the distance you need to overcome to deliver the service is measured in terms of the shortest path distances. And I'm positive everybody knows how to compute a shortest path in a network at this stage. If you don't have any idea of what this means, please go back to perhaps your undergraduate texts, and there you will see certain methods on networks for computing shortest paths from a given node to some other given node. You know, if the arc lengths in the network are non-negative, in that case, of course, the Dijkstra's method will be quite useful. It will do the job for you. In fact, Dijkstra's method can be extended with a slight modification to compute a shortest path from a given node to every other node in the transportation network. Okay, that's a slight modification. Now, sometimes you're also going to need the distance or the shortest path distance from any node to any other node. That's called the all pairs shortest path distances. So you need to generate these distances between every possible pair of cities in Turkey, for example. Since we have 81 cities, that means we need to generate an 81 by 81 matrix. It's symmetric, so you can truncate the lower half of the matrix. Nevertheless, it's a lot of numbers, and these things can be done quite efficiently. Either you can repeat the Dijkstra from one to everybody else method. Using that method once for every home base city. Okay, so you may have to repeat the same method once for every city, once for every one of the 81 cities in Turkey. And the other method you can use, for example, Floyd's algorithm or Danzig-Ford algorithm. These methods work with certain matrices. They modify the matrices as you go along. But anyway, generating the shortest path distances between all pairs is always possible. So I just want to give you that initial information because we're going to assume that these distances will be available in some way. So what we're going to do is we're going to assume there's a certain network under consideration which represents some sort of a transportation network. And there are certain kilometers or lengths associated with these arcs in the network. These are undirected arcs. So I suppose the lengths are 5, 10, 6, 7, 6, 8, 11, 3, 14, 18, 20, 10, 5, and 30. I'm just making up these numbers. Don't try to give any meaning to them. And these nodes in the network are certain cities, for example. And suppose you want to deliver, say, supplies to these destinations, to every one of these nodes on a regular basis every week. Okay? And you have truckloads of delivery. And the truckloads of delivery you need for this one is, for example, 20 tons per week. This one is 30 tons per week. This one is 10. This one, 5. This one is 40. This one is 25. This one is 60. And that one is 100. And this one is 50. Now, I'm going to interpret these numbers as being the number of trips you are going to make to these nodes. So 20 means you need to go there 20 times per week, for example. Okay? Or if that sounds too much to you, let's take it to be a year. Okay? Let's just change it to a year. So you want to visit this particular point 20 times per year. This one 30 times per year, so on and so forth. So the red numbers are the number of trips. And the question is, where am I supposed to situate myself for delivering these services to minimize the total distance I cover during this movement. Of course, why am I interested in minimizing the total distance? Because normally your transportation costs are proportional to the amounts of distances you cover, and that's the reason. Now, if we're talking about a single depot, for example, a depot is going to house all the products you're going to deliver, and suppose you placed yourself, for example, here. Let me give names to these nodes. Let's call them, for example, node number 1, number 2, number 3, number 4, 5, 6, 7, 8, and let's call this one 9. If I place myself on node number 9, what would be the total transportation distance I would have to cover to provide all this service? It's quite straightforward. Let's just compute that. Sorry, this will be node number 9. Now, the number of trips for node number 1 is 60. For node number 2 is 100. Number 3 is 20. Number 4 is 30. Number 5 is 10. Number 7 is 40. Number 8 is 25. Number 9 is 50. And I'm supposed to have the distances here. From 9 to 1, what is the shortest distance? Well, I guess along this path, right? So I would be going along this path. That would be 60. 10. To number 2, it seems that 6 is the shortest possible way of getting there. For number 3, I have 6 plus 7, or 18 plus 16, or probably other stuff, but this seems to be the shortest. So that's 13. What about number 4? What is the shortest here? 6 plus 7 is 13, plus 8 is 21. Is that the best? Seems to be, yeah. I'm just doing this by inspection. Of course, for a large network, you might have to use one of the known methods to compute these distances. All right, for number 5, 6 plus 7 is 13. That's 19, but this is 18. That seems to be better. Okay. Number 6, 18 plus 3 is the best, I guess. 21. Number 7, 20 is the best. Number 8, it will be 25. For number 9, it's 0. So this will be 10 times 60. That's going to be 600. That's also 600. This is how much? 260. Then we've got 630. We've got 180. Another one is 105. That one is 800. Wow, that's large. Are we sure about, yes, well, that's 20 is large. 25 times 25 is how much? 625? How much? 625. And this one is 0. So if you add them up, you get whatever you get. Somebody quick can do it. How much? 3,500. 800. So that's how much distance you cover for this particular setting. So the question is, well, am I really doing well in this case? Can I do better if I place myself, for example, on node number 5 or perhaps on node number 2? We have no benchmarking. Of course, we can try each one separately and find out. There's also the remaining question. I don't have to put myself in one of these cities. What if I permit myself to locate my depot along the way somewhere? Then I'm expanding my set of choices. And when you have more choices, of course, you cannot get worse, because the set of choices you have now along the arcs includes the set of choices you had before, which are the nodes. Okay? So one of the arc locations, the interior to the arcs, could perhaps be better. It can, considering a larger set of alternatives will not ever make you worse. So we don't know. And it requires some sort of an analysis. And of course, we would like to somehow formalize these ideas into formulating a meaningful problem here, and then somehow we will analyze and solve it. Okay? But half of the way is to formulate something in a meaningful way. So here's the combinatorial formulation of the problem. I'm going to locate a point X. The point on the network at which we locate the service facility. Now, I have two possibilities here, which gives rise to two different formulations. One possibility is to restrict X to node locations, in which case, of course, you've got 9 possible locations to put the depot at. The second case includes all points along all arcs in addition to the node locations. Now, the second case, of course, may possibly give you a smaller cost or smaller movement solution. Okay? Movement in terms of the total distance covered. So, and the data of the problem, I'm going to just call Wi the number of trips you make to node I. I'm assuming everybody or every node here is a demand node. Of course, Wi can be 0 if that particular node is not a demand point, but in general, it's a non-negative number. Okay? In our case, in the example, each Wi is positive. And what else do I have? distances. Okay, let me call by this notation dx vi. Vi stands for the ith node, and dx vi stands for the length of a shortest path connecting point X to node Vi. All right, so given this information, my formulation is the following. Minimize Wi times dx Vi. So you're multiplying the distance from x to Vi, which is the shortest path length, by Wi, and you sum this up over all nodes 1 to 9, and you try to minimize this function. Wi are given numbers here, okay? dx Vi are not given numbers, but they are computable numbers. If you know x, then you are able to compute it. So given this function, you want to minimize this function over all possible choices of x. So if you restrict your x to the set of vertices, let's just call V to be the set of vertices. So in this case, V is the set of nodes V1 up to V9. Vertices and nodes are the same name for, different names for the same thing. So in this case, we restrict ourselves to node locations, and we want to minimize that. In the second case, so this is one problem, this is the second problem. It's the same objective function, except that x will be any point on the network, consisting of all points along arcs as well as node locations. Okay. Now, the first problem is called the vertex restricted medium problem, or node restricted medium problem. The second one is called the absolute medium problem. The vertex restricted medium problem is computationally trivial. What do? You just assume yourself to be situated at any one of the vertices. You compute your objective function value, and then once you repeat this for each home base, you just choose the smallest. Okay, that's quite trivial. The second one, unfortunately, is not that trivial unless you do further analysis. First of all, the second one, the difficulty with the second one is you've got infinitely many points along an arc, which means that we're talking about an infinite search space for x. And we have no idea which one might qualify as an optimal. Okay? So it just requires a lot of other analysis. But this is not the only problem you can pose here. Sometimes we've got different problems. which is more appropriate for emergency service provision. For example, the network we had before, suppose that represents a metropolitan area with those arcs being road segments, okay? And suppose you're interested in delivering, say, fire protection service to these nodes. These nodes are, in fact, areas of importance. You want to somehow deliver fire protection service to these nodes whenever there's a fire. Now, you don't have oftentimes fire all the time. Sometimes they all come in abundance, but nevertheless, it's a rare, well, it occurs from time to time, okay? So you don't make a trip to every one of these nodes 30 times or 40 times or 100 times every year. You don't do that. However, whenever there's a fire incident at one of these locations, you want to get there as quickly as possible within a reasonable amount of time. For example, if you get there, say, within 20 minutes, fine, you can provide a pretty good service, I guess. But if you get there in 40 minutes, maybe everything will be all gone by the time you get there, okay? However, you know, the sooner you get there, the better. The quickest is the best, okay? Now, if you don't differentiate between people living at one locations and from people living at other locations, human life is the same for regardless of the status or whatever. Of course, we want to deliver the service in the quickest possible way so that everybody will be covered within the best coverage distance that we can achieve, okay? That requires a minimax type of formulation. It's really quite different from the total cost formulation in the previous example. In that case, you make many trips, so you want to somehow minimize the cost of delivery, whereas in this case, forget the cost. You want to get there to save human life. That's important, okay? So, in the emergency location situation, now I want to minimize the maximum of these distances. In other words, if I put myself at point X, if that's the location of the fire station, and if the delivery to vertex VI is made in the quickest way along this path, along the shortest path, so it will take time proportionate to this distance. Now, when you put yourself at X, whichever one is the largest of these, out of those 9 vertices, you are looking at the farthest one. That's the one which is farthest away from you. So if you're going to be there, say, within, say, 20 minutes, then the farthest one, if you achieve that 20-minute threshold value for the farthest one, you certainly achieve that for everybody else, okay? So the farthest one is your most important one. That's the value. So rather than a summation here, we have a maximum operator. And you want to minimize that over all possible choices of X. Again, if X is restricted to the vertices, this is rather straightforward. You just evaluate the objective function at every vertex and choose the best, okay? So that's the vertex restricted one center problem. In the other case, it's the same problem, except that X can be any point along the arcs. Again, you minimize the maximum of the distances between X and VI. That's the absolute center problem. Okay. Now, even though I posed these problems in terms of absolute distances to get from x to every one of the vertices, in the literature, people typically have weights here, which are not necessarily the weights we had in mind in the previous example, but these are weights that somehow could attach different levels of importance to different vertices. For example, if property value is at stake, a high-rise mall at, for example, Çankaya, a rather dense region, could be more valuable than, you know, a small cottage somewhere else. Now that, I say it with qualification because for me human life is more important. Nevertheless, people have assumed there are certain weights present in front of these distances just to make it more general. So let's stick with the more general case. Whether or not it makes sense to you, that's another matter, okay? All right, so let's just put that also here. If you're not very comfortable with weights being attached to levels of service for emergency cases, you may just disregard them. But then I have another model where you replace actually Wi with a monotonic disutility function, which actually increases monotonically as the distance is getting larger and larger. That's the most general situation. If time permits, we will go into that. You have a question?
In emergency problems, maybe population can be raised.
Okay, fine. Yeah, yeah. I think that's a good interpretation. If Wi represents the population density at vertex Vi, then of course you want to somehow be closer to more dense districts than others. Still, I have problems with that you know, argument, not with your argument, but with other people's arguments. Yes?
When we get the disutility function, we replace both the weights and the distance with that, right?
No, the disutility, for example, if you call it Fi associated with vertex I, you evaluate the disutility at the distance value.
So
it's monotonic.
Yes, but it comes in the place of Wi times distance.
Right. So, for example, Wi times distance, if this is the distance, and if this is Wi times d, this is the disutility you have as the distance is increasing, whereas in this case, of course, it could be any kind of a monotonic function, okay, as a function of the distance. All right, anyway, this is just to sort of motivate what sort of facility location problems we might have under consideration. And of course, this both examples were one facility examples, but sometimes you may have to place many of these facilities, in which case we have the so-called P-median facility location problem or P-center facility location problem, where P is any positive integer. Of course, it doesn't have to be greater than the number of vertices under consideration, because in that case you would place one at every vertex, in which case the coverage is within zero, instantaneous coverage, okay? Within the approximations of the model, of course. All right. So let's now start going into the analysis of this problem. To properly analyze such problems, to be able to generate solutions, first, I need to somehow formulate the general notion of networks or graphs into the so-called embedded networks. Without that, we cannot really get anywhere, okay? Actually, let's change that G to N, because that's what I used here. So let N cap, V cap, E cap be an undirected finite network with vertex set V cap. Suppose you've got N vertices. Okay. And edge set E cap consisting of undirected edges Vi, Vj cap for some index set I consisting of index pairs ij for which Vi, Vj exists. Exists means in E cap. Okay? You don't have to have an edge between every possible pair of vertices, but whenever you have, you put those index pairs into the set, index set I. Okay? Now, here's an example. In this case, of course, we've got V consisting of vertices V1, 2, and 3. Except that I use caps for these. And the edge set consists of the undirected edges V1, V2, V1, V3, V2, V3 with caps. In this case, I have a complete network on 3 vertices. Complete means you have a possible edge between every possible pair of vertices. In general, you don't have to have all the possible edges. Okay? Now, from here, what we want to do is we want to define an embedded network. I forgot to mention one thing. Let's also assume there are edge lengths. Assume edges have positive lengths denoted by, say, Lij for edge, Vi, Vj. Okay? So, an embedding of N cap with vertex V set V cap and edge set E cap in some space S where S could be any space. Nevertheless, if you want to somehow relate to it, you may take it to be R2, the plane. Okay? So, an embedding of N cap in some space S is a set n in the space S such that n is the union of the sets Aij corresponding to index pairs ij that are in the defining set for the edges, okay, where Aij is the image of a one-to-one mapping, say Tij, of the unit interval zero, 1 into S such that the mapping associated with edge VIVJ or Tij evaluated at 0 is equal to Vi, and Tij of 1 is equal to Vj, with, pardon?
Vi cap, Vj cap.
No, they are Vi and Vj, with V1 up to Vn being distinct points in the set S or in the space S, representing V1 cap up to Vn cap respectively. Now, this is a complicated definition, so we'll go through that a little bit. It's quite formal, and you won't see that sort of formalism in the location literature unless you're interested in mathematical maturity, such as myself, okay? It requires, because in order to develop advanced concepts, you have to be formal. Otherwise, it doesn't go anywhere. Some people, they suffice with that, but if you want to go deeper, then you have to somehow structure whatever you are talking about. Okay, so anyway, I'm going to explain to you what I mean now. So, suppose my n cap is this particular graph with vertices v1 up to v5 with caps and edges, as you see in the picture, and you've got certain lengths associated with the arcs. Okay? This is not an embedded network. It's just a regular network in the sense you already know of up to now. Now, what we do here is we first of all consider a particular space. In this case, I'm going to take S as, for example, the plane. Okay? So in the plane, what I'm going to do is, I don't have to have axes, nevertheless, that's just have these axes, I'm going to have 5 distinct points representing these vertices. How did I choose them? It doesn't matter. You just choose 5 distinct points. They shouldn't coincide. Then, for each ij, my set I in this case consists of the pairs 1, 2, 1, 4, 1, 5, 2, 3, 2, 4, no, not 2, 4, but 2, 5. What else? 3, 4, 3, 5, and 4, 5. I adopt the convention, these are undirected pairs, I adopt the convention that I always list these things with lower index first, higher index second, okay? Then you will not make mistakes. Otherwise, it's easy to omit certain edges, okay? Anyway, those are the pairs. So for each pair, I'm going to define a t function. For example, t12. I need to have a t12. Now, aij is the image of a one-to-one continuous, this should be continuous, is the image of a one-to-one continuous mapping Tij of the unit interval 0, 1. So T12 is mapping the unit interval 0, 1 into S. It's a continuous mapping. It's a one-to-one mapping, so it's invertible. Okay, one-to-one means it's into invertible. It's not onto, but rather it's into. If you don't know what the difference is between onto and into, forget that. It's not important at this point. But what T12 does is it picks a number from the unit interval and it assigns a point in S, or in the plane, okay? Because it's continuous, it turns out that when you look at the set of all points assigned by T12 to the set of points in the interval, that set gives you A12, which means that A12 is some sort of a point set, such as this one. It's continuous. It's actually a rectifiable curve in the plane, but you probably don't know what rectifiable curves are, so I'll forget that also. But this is a continuous mapping, and that's the image of that mapping, okay? What do I know about T12? I don't know anything. The only thing I require is that it be one-to-one, it be continuous, and 0 gets mapped into V1, and 1 gets mapped into V2 in this case, okay? And if I pick a point X here, that's too small for the camera to capture, nevertheless there's an X there, that will be the image of some number in the interval 0 to 1. So it will be, for example, some real number R in that interval, okay, whatever. So I do this for 1, 2. So let's have that. I do it for 1, 4. I do it for 1, 5, etc. You just follow all the indices and you generate all these things. Okay?
Does those functions have any relationship between them?
They don't have to. we don't want them to intersect at any point other than vertex locations. I did not say that yet, but I'm going to say it, okay? Other than that, I don't want to assume any particulars about these functions, but this formality allows me to speak of points along edges, whereas in a regular network, we don't have such points. What we have is only pairs, okay? Pairs are different from set of points. So anyway, with that formalism, we are going to be able to start analyzing these things. Actually, later on, I'm going to switch to rather informal arguments, but in the background, always keep in mind that there's a formal setting where these arguments are valid. Okay, that's important. We're out of time, so I'll just stop here. On Wednesday, we'll do some examples and more interesting stuff. This formalism should not make you, get discouraged, okay?